Hello everyone, in this small video we are going to quickly see the overview of complexity classes P and NP of different algorithms. So what do you mean by P, what do you mean by NP hard problems and NP complete problems are going to be introduced in this video. So what do you mean by class P? It is nothing but the algorithms whose running time will be defined in polynomial time terms. What do you mean by polynomial time? It can be n square, n cube, or 3n square, or it can be 1. Alright, so these are the complexities of polynomial time algorithms. So if you look at any of the search algorithms or sort algorithms, it will be having the complexities like 1 can be n log n square, n cube. In the case of matrix multiplication, we'll be needing n cube number of operations. So these are polynomial time algorithms. So those are classified as class P algorithms because they are polynomial time computable. Alright, this is the formal definition. So if P of n, Q of n are polynomials, means if we have two algorithms whose running time are polynomials, whose worst case complexities can be represented in terms of polynomial. So if you are able to combine them algorithm, the resultant algorithm is going to be polynomial time computable because the polynomials are closed under addition, operation, multiplication and composition. So if P of n, Q of n are two polynomials, then P of n plus Q of n is also going to be a polynomial. P of n dot Q of n will be a polynomial. P of Q of n is also going to be a polynomial. So we can combine or compose polynomial time algorithms to develop a new polynomial time algorithm. So it is important for us to have complexities in terms of polynomials so that the time complexity of the algorithm is minimum or small. So if you look at towers of Hanoi problem, we know that the worst case complexity of that, the best case complexity of that algorithm is 2 power n minus 1. 2 power n is not polynomial, it is exponential time. So it is not a class P algorithm, it is non-polynomial time algorithm. So in this screen we are defining a new set of problems called decision problems. So what do you mean by decision problem? The computational problems for which the output is either yes or no. Means so we'll be finding whether is there any solution for this problem or not, or whether the problem can be solved or not. So the output is going to be true or false or 0 or 1 or yes or no. So for example, if you are given with a string t and a string p, and if you are asked a question like does p appear as a substring of t, alright, means we are supposed to search for the string p in the text t. Alright, so the answer is going to be yes or no. Yes. So this is known as decision problem. It will be having only two results, positive or negative, or successful, unsuccessful. So another example, if you are given two sets s and t, and do s and t contain same set of elements, so the answer for this problem is also going to be yes or no. So this is a decision making problem. And if you look at the third example, given a graph G with integer weights on its edges, means we are given a weighted graph and an integer k, and does G have a minimum spanning tree of weight at most k? If you look at this problem, and so this is talking about the minimum spanning tree. Alright, in minimum spanning tree we will be finding the minimum spanning tree and the minimum cost, but this problem is a slight deviated one. It is asking us to check whether that minimum cost is k or not. So the answer is going to be yes or no. It's not going to be finding the minimum cost spanning tree, which is a graph algorithm. It is going to be having polynomial time, but this is a decision making problem. Alright, so if we can show that decision problem is hard, then its related optimization version must also be hard. What is hard? It is not polynomially time computable. So complexity P. So if it is polynomial time computable, then it is class P. If you are having a decision problem and if that decision problem can be solved in polynomial time, then it is of class P. So what is mean by accepted, non-accepted here? The complexity class P is a set of all decision problems, and here we are using a term languages. This term languages will be used mainly in theoretical computer science terms, where we'll be defining each and every problem as set of languages. Say for example, if we take English as a language, it has 26 alphabets, and we'll be having different strings or different words or a number of words. And in the case if you are given with a string, and our aim is to find whether that string is part of English language or not, that is known as the decision problem. The answer is going to be yes or no, or the answer is going to be the string is an acceptable string of English language, or it is not acceptable. So it is true or false kind of answer. So it is known as decision problem. That's why we are using languages also as set of to represent the decision problem. And if L, that can be accepted in worst case polynomial time. And if you look at these terms, accepted in worst case, so accepted means we are going to talk only about the positive results. Alright, we are not going to talk about the failed searches or negative results. And in worst case we are going to have polynomial time. So it's not about best case. In worst case it should be having a polynomial time algorithm. So these algorithms are going to be called as class P algorithm. Alright, if there is an algorithm A, if X is L, X is nothing but the input, and the algorithm A outputs yes, means it is accepting that string or giving a positive output for that string in P of n time. P of n is a polynomial. Alright, so n is the size of the input. So based on that we are defining a polynomial to represent the complexity of this algorithm A. So in worst case, if it computes the result in polynomial time, then that is known as class P problem. So what is class NP? So in layman terms you can remember this as non-polynomial time computable problem. Alright, the complexity class NP is a set of decision problems or languages L that can be non-deterministically accepted in polynomial time. What do you mean non-determinism? So there will be confusion. So we cannot definitely say that it will be. So in all the cases it will be giving polynomial time complexity. So it is non-deterministically accepted by in polynomial time. So if there is a non-deterministic algorithm A, similar to the previous definition, X is the input, L means the language, then input X, the set of outcomes to choose calls means, so it will be having different options to choose. So if it is positive in polynomial time, then if the algorithm is non-deterministic, then it is known as NP problem. So choose B is a function or operation that chooses in non-deterministic way a bit that assigns it to B. So what is non-deterministic? We do not know whether it will choose 0 or 1. Alright, so in some cases it will be giving polynomial time. If that happens, then it is known as non-polynomial or NP class problem, because in the case of P, in worst case it is going to be polynomial, means in any cases it cannot have any other, so it is going to have a polynomial time complexity. So in NP, in some cases it will be having polynomial time, otherwise it is not. So it is NP class problem. So here we are going to see some of the examples of NP problems. What is Hamiltonian cycle problem? What do you mean by Hamiltonian cycle? We'll be given with a graph and we'll be asked to find whether we have a cycle. What do you mean by cycle? The starting and ending vertex is going to be the same, but Hamiltonian cycle is different. So it should go through all the vertices of the graph exactly once and coming back to the starting vertex. It is going to be a tour that starts from one vertex and ends in the same vertex, but it has to cross all other vertices exactly once. That is Hamiltonian cycle problem. And how can you make it as a decision problem? So by asking whether we have a Hamiltonian cycle in this graph or not. So if you are given with the graph and the question is like, so whether this graph is having a Hamiltonian cycle or not, that makes it a decision problem. So this is NP problem. There is no polynomial time computable, there is no polynomial time complexity for this problem. Second is Boolean circuit problem. So it's a directed graph where each and every node is having the property of a logic gate. The logic gates are AND or NOT. The Boolean function means, so the output is going to be true or false. In the case of truth table of AND or NOT gates, we will be having 2 inputs and 1 output. In the case of AND and OR, NOT is going to have 1 input and it is going to negate that input. So it is going to be a Boolean. If you are giving 0 as input for NOT, it is going to give 1 as the output. Alright. So the incoming edges for logic gate corresponding to the input for Boolean function. represented by that gate in that node, and our aim is to find, for example, if you are given with a circuit and the output is going to be 1, so what should be the input of the input to that gates? So what should be the input to the circuit? So this is known as Boolean circuit problem. It is going to take zeros and ones as input, but if you are given with a circuit, you should find the possible input so that the output is going to be 1. So this is known as circuit satisfiability problem. This is one of the examples of NP problem. Alright, the third one is vertex cover problem. What do you mean by vertex cover? So we will be given with a graph and we need to find a subset of vertices in such a way that and the C should contain at least one vertex of each and every edge. Alright, so that is known as vertex cover problem. So it is a decision problem that takes a graph G as input and one integer K as input, and it will ask whether is there a vertex cover of G containing at most K vertices. So K is the upper bound of that number of vertices in the K in the vertices in the set C. So our aim is to find whether we can construct a vertex cover with a maximum K number of vertices in them. So this is also one of the NP problem. So what is polynomial time reducibility? And the complexity class NP is useful if it formally captures a host of problems that may be believed to be computationally difficult. What do you mean by this one? So if you say a problem is NP, which means it should be a hard problem, or it is difficult to compute the complexity of the problem. So polynomial time reducibility is that, and if you are able to convert or reduce a problem in NP to any of the problems that can be computable in polynomial time, then it is known as polynomial time reducibility. Alright, say we have a language L, it defines some of the decision problem. So polynomial time reducible to language M if there is a function f computable in polynomial time. So we are going to find that function f, so that is going to be computable in polynomial time, that takes an input x to L and transform it to an input f of x of m, such that x is in L, and if f of x is L and L is polynomially reducible to m. So if you are able to find a function f that reduces the complexity into the polynomial time complexity, then it is known as polynomial time reducibility. Alright, so NP hard and NP complete. The language M defining some decision problem is NP hard if every other language L in NP is polynomial time reducible to M. So if all the other languages L in NP is polynomial time reducible to M. So we are going to say M is NP hard if the all other NP problems in L is going to be polynomial time reducible. What is polynomial time reducible? We will be having a function f which is computable in polynomial time, that will be reduced x to f of x as an input to M. So then M will be a NP hard problem. So L polynomial time reducible to M, and if all L's are NP are non polynomial time computable, then M will be an NP hard problem. So if a language M is in NP hard, already M is NP hard, it is also in the class of NP. So M is itself an NP problem and it is NP hard itself, then we can say M is NP complete, which means an NP complete problem is, in a formal sense, one of the hardest problems in NP. So NP complete is an NP problem and the hardest NP problem that can be solved. So as far as polynomial time computability is concerned, so based on the polynomial time computability is concerned, NP complete is one of the hardest NP problem that can be solved in polynomial time. So if anyone finds a deterministic polynomial time algorithm for even one NP complete problem, then P will be NP. So all the NP problems will become polynomial computable problem, or P can be termed as NP problems, which means if one NP complete problem can be solved in polynomial time, if one NP complete can be converted into a P problem, then P will become NP. So that's all about NP hard and NP complete problems. So these are the different classes of problems: P, NP, NP hard, and NP complete problem in terms of algorithm analysis. And this kind of analysis will help us to identify the different classes of algorithms based on their complexity and computational difficulties. And the NP hard, NP completeness is one of the research areas for decades. Thank you for listening.